Okay, so here's a thought experiment for you. What if the very fabric of reality, space, time, matter, all the forces, what if it wasn't just this passive backdrop for everything happening?
Like it's more involved.
Exactly. What if it was intrinsically linked to how information itself is processed, like fundamentally computed?
Ah, so you're asking, what if physics and computation weren't separate things at all?
Yeah. What if they were like two sides of the same coin, both emerging from the same deep fundamental principles?
Well, that's precisely the kind of mind-bending idea we're diving into today. There's a revolutionary new paper proposing exactly that.
It sounds pretty out there. We're going to be digging into excerpts from FCHP, Foundations of Finsler Coherence Hyperfractal Phase Space and Coherence-Based Computation. It's by Philip Lillian, just published August 2025.
And it really is a fundamental rethink. This isn't just, a new theory within physics or a proposal for a faster computer. It's suggesting a complete paradigm shift.
A unified ontology, is that the right word? Where physics and computation are basically built from the same stuff.
Precisely. A unified physical and computational ontology. Matter, energy, logic, all fundamentally united at the deepest level.
Okay, so our mission in this deep dive then is to really unpack the details of this. FCHP, Finsler Coherence Hyperfractal Phase Space. It's quite a mouthful.
It is. And it's a bold framework, no doubt about it. It challenges our core understanding of reality and potentially opens doors to what the paper calls a post-digital era of computation.
Post-digital. Wow. So we'll explore how FCHP tries to redefine everything: gravity, time, even logic gates, and computer memory, all through this central concept of coherence.
Yeah, coherence is the key. And maybe an analogy from the paper itself could help us, get started.
Please, an analogy would be great right now.
Okay, so imagine reality is this vast, shimmering, multi-layered tapestry. But it's not static like a museum piece. It's woven from these dynamic threads of coherence. It's constantly shifting, evolving, alive almost.
Okay, a dynamic tapestry of coherence threads. I'm with you so far.
Now, in this tapestry, what we perceive as fundamental things, particles, forces, even the flow of time, they aren't separate entities woven in. They're just different patterns and textures that emerge from the way these coherence threads interact, how they knot together, twist around each other, flow.
So particles are like really tight knots, and forces are maybe the tension in the threads.
That's a good way to think about it, yeah. It's the patterns, the configurations.
Yeah.
The universe isn't just there. It's an active process, this constant unfolding dance of coherence, which is essentially information.
Right, and this is where the computation part comes in, isn't it?
Exactly, because computation, in this view, isn't about manipulating something separate, like flipping tiny voltage switches on a silicon chip that sits apart from reality.
No,
It's about intentionally creating and interacting with these coherence patterns within the tapestry itself, making them resonate in certain ways or interfere with each other or form stable knots using those patterns to encode and process information directly within the fabric of reality.
so we're not just watching the tapestry. We're learning to weave, like manipulating the threads ourselves to create complex, self-organizing designs that can hold memory or perform logical operations.
That's the idea. It's an active, dynamic relationship between existence and information processing. A really profound shift.
It really is. But maybe, can we make that jump a bit more concrete? How does manipulating coherence patterns actually translate into something like, say, an electron or the force of gravity we feel? It still feels a bit abstract.
It's a fair question. It gets right to the core of FCHP. We're so used to thinking of particles as little points or forces as pushes and pulls acting on things.
By the classical picture.
But in FCHP, those aren't the fundamental building blocks. They emerge. So using the tapestry analogy again, maybe a particularly stable localized knot or whorl in the coherence threads is what we perceive and measure as an electron. And maybe a large-scale pattern where threads are consistently drawing together over a region, structuring the surrounding coherence, that's what manifests as gravity. It's not a force acting through space, but a property of the space's coherent structure itself.
So it's all about the underlying pattern and the flow of this coherent stuff. The properties emerge from the arrangement.
Exactly. It's a shift from objects and forces to patterns and dynamics. So let's unpack this whole new physical reality FCHP proposes.
All right, let's dive into part one. We're looking at how FCHP fundamentally redefines physical reality. And the first step is this huge paradigm shift away from classical spacetime.
That's right. The FCHP framework essentially says, okay, that idea of classical spacetime, the fixed four-dimensional stage where physics happens, Let's replace it.
Replace it entirely. With what?
With something radically different.
Yeah.
Instead of that rigid grid, imagine the foundation of the universe is more like a dynamic, structured fluid. FCHP describes it as a direction-dependent, fractally scaling coherence geometry.
Okay, break that down. Direction-dependent.
It means the properties of space itself, how you measure distance, for instance, can actually change depending on the direction you're moving or even looking. It's not uniform.
Wow. And fractally scaling.
That means it has a kind of self-similar structure at different scales, like a coastline, where the patterns you see up close repeat in a similar way when you zoom out, but it's built into the geometry itself, an inherent complexity at all levels.
So the very fabric of space isn't smooth and simple. It's complex, directional, and patterned.
And the truly groundbreaking insight here, the core idea, is that coherence itself is the fundamental substrate. It's not just a property of fields or particles. It's the actual stuff from which everything else emerges.
That's a huge claim, because it means things we usually think of as fundamental aren't.
Exactly. Things like dimensionality, how many dimensions there are, or the fundamental forces, mass, even time itself. In FCHP, these are no longer primitive assumptions. They aren't just given.
So how do they arise then?
They emerge dynamically. The paper calls them modulations of coherence gradients. Think back to the tapestry. These are like ripples, flows, or variations in the density and alignment of those coherence threads.
Okay.
And these gradients are what give rise to everything we perceive. Space isn't passive. It's inherently anisotropic, that direction-dependent quality, and it actively shapes physical structures through these coherence flows. The medium itself dictates the rules.
Now, mathematically, how do they describe this? You mentioned it's not the usual geometry of general relativity.
Right. Classical general relativity uses Riemannian geometry. In that system, the rule for measuring distances depends only on your position. Like the curvature is fixed at each point on a surface.
Okay.
FCHP, however, uses Finsler geometry. This is a more general framework where the metric depends on both position and direction.
So the directionality is baked right into the fundamental math.
Precisely. Your speed and direction can change the effective geometry you experience. It's like the terrain shifts depending on how you move through it.
And why is that a better fit, according to the paper?
Because this inherent anisotropy, this direction dependence, makes Finsler geometry naturally suited to model key quantum phenomena that are awkward in Riemannian space. Things like those directional coherence gradients we mentioned, quantum spin, which has an inherent directionality, and even something called torsion, which is like a twisting of space-time.
Torsion, like space itself can be twisted?
In a sense, yes. Finsler geometry provides a more natural home for these kinds of effects, offering a better foundation for physics based on quantum coherence.
So these coherence gradients, the flows and variations are central. The paper calls them the true cause.
Yes, that's a key assertion. They're defined as directional flows or differentials of field coherence across hyperfractal scales. Think subtle currents in the coherence tapestry.
And these currents are responsible for forces and even space-time curvature.
FCHP argues exactly that. Instead of forces causing particles to move or mass curving space-time, it's these underlying coherence gradients. They're the fundamental movers and shapers. They sculpt the fields and particle behavior. It flips the causal relationship we usually assume.
That's a big shift. What about dimensions? You said dimensionality isn't fixed either.
Right. Forget the fixed 3+1 dimensions we're used to. In FCHP, dimensionality is dynamic. It actually unfolds.
Unfolds.
The hyperfractal scaling. The idea is that new dimensions can emerge through nested coherence breakdowns. Imagine zooming into the structure as you cross certain thresholds, new layers, new dimensional degrees of freedom become accessible.
So reality could have different effective dimensions depending on the scale or energy.
That's the implication. It allows for a potentially smooth unification of physics across scales, from the quantum world to the cosmos, without awkward extra dimensions just tacked on.
And these dimensional steps, they're quantized, like discrete levels.
Yes, each step is a hyperfractal threshold, a point where new forms of coherence resonance can occur. And these steps are discrete, quantized, and governed by something new called Noetherian Finsler Numbers, or NFNs.
Okay, NFNs. Sounds important. What are they?
They're defined as quantized coherence invariants. Think of them as fundamental conserved quantities, but not in space-time in this more complex Finsler coherence space.
Like conservation of energy or momentum, but for coherence.
Exactly, but much more general. They extend Noether's famous theorem, which links symmetries to conserved quantities, into this coherence-based algebra. It moves beyond classical space-time symmetries.
So even in this fluid changing geometry, the NFNs provide some underlying stability conserved rules.
Precisely. They are the quantized backbone of FCHP's geometry, ensuring coherence is conserved in specific ways across transformations.
And how do they show up? What do they represent physically?
They can manifest in diverse ways. An NFN could correspond to quantized angular momentum, or a topological charge, or one of those specific dimensional steps, or even the phase of a field. They're the fundamental quantum numbers of this coherence geometry.
Okay, so NFNs structure the dimensions and conserve coherence. How does this reframe forces and time?
Well, all the classical forces, electromagnetism, nuclear forces, gravity, are seen as emerging from these coherence gradients, structured across layers defined by the NFNs. They're structured reductions of coherence gradients.
Not fundamental interactions, but patterns of coherence flow.
Yes. And gravity gets a particularly radical reinterpretation.
You mentioned this earlier. It's not a force, not space-time curvature.
It's seen as a coherent structuring operator, a fundamental way coherence organizes itself. It's an intrinsic property of the coherence fabric, how it tends to pattern itself, rather than something external acting on it.
That's hard to grasp, but profound. And time.
Time also gets completely redefined. It's not a universal clock ticking uniformly for everyone.
Okay, so what is it?
It's described as a vector field of coherence phase transitions. It's directionally embedded within the FCHP structure itself, and its flow is modulated by chirality handedness, like left-to-right spirals, and something called phase spin torsion.
So time is like a directional flow within the coherence tapestry. Its rate and direction can vary.
Essentially, yes. It's part of the dynamic geometry, not separate from it, modulated by the local coherence structure.
This also ties into spin, right? You mentioned a unified spin torsion chirality structure.
Exactly. Quantum spin, which often feels like just an abstract quantum number, is proposed to be a fundamental geometric property of the FCHP phase space itself.
Like the space inherently has spin.
In a way, this property is expressed through torsional flows, those twisting motions in the geometry and chirality vectors, describing that inherent handedness.
So things like spin, or why some interactions favor left-handedness over right-handedness, parity violation, these aren't weird quantum exceptions.
According to FCHP, no. They are emergent features, directly reflecting the underlying geometry of this Finsler space. They're natural consequences of the shape of reality.
And just to round this off, how does this relate to Einstein's general relativity, our current best theory of gravity? Does FCHP discard it?
No, it actually recovers general relativity, but views it as incomplete specifically, as a low coherence approximation.
Ah, so GR works well in situations where these deeper coherence effects aren't dominant.
That's the idea. The familiar curvature of spacetime in GR is replaced by the more fundamental directional coherence curvature of FCHP.
And quantum effects fit in more naturally.
Yes, things like entanglement or quantum phase transitions aren't separate mysteries. They're modeled as topological transformations, shifts in the connectivity or structure within this Finslerian hyperfractal space. It aims for a more unified picture where quantum behavior is a natural consequence of the underlying geometry.
Wow. Okay, that's a lot to take in. The conceptual shift is enormous, replacing space-time, redefining forces, time, dimensions, all emerging from coherence.
It's definitely a radical proposal, a whole new foundation for physics.
But, grand ideas are one thing. Making them mathematically rigorous is another. So how does FCHP actually formalize all this? Can we peek under the hood at the math without getting completely lost?
We can certainly look at the key mathematical structures. The paper doesn't shy away from the formalism. It starts with the very definition of distance, the line element RS. In FCHP, it's based on a Finsler Coherence norm, FXY.
FXY. So it depends on x, the position, and y, the direction or velocity vector.
Exactly. That yoid dependence is the core of Finsler geometry, making paths inherently direction-dependent right from the start.
Okay, so the geometry itself knows about direction. What about the coherence part?
That's captured primarily by the coherence tensor, let's call it Jake. This tensor isn't just about curvature, like in GR. It specifically modulates the coherence gradients.
So it governs how coherence flows and changes.
Precisely. It governs things like intrinsic twist, that spin torsion idea, how phase gradients propagate, and even chirality selection, the handedness. It's the mathematical engine driving the anisotropic coherence dynamics.
And the dimensions. How does the math describe them unfolding?
Through the hyperfractal dimensional cascade, there's actually an equation for the emergent dimension at a level n, DNN. It involves logarithms of coherence eigenvalues at that level.
Eigenvalues, the characteristic values of the coherence field.
Sort of, yeah. Relative to a base coherence quantum plus a starting seed dimension. The key is that it mathematically builds up dimensions step by step.
Does it give examples?
It does. It links dimension levels to the NFN levels, like NFN1 gives 1D, NFN2 gives 2D, NFN3 is 3D space, NFN4 integrates time for 4D, NFN5 adds spin torsion fields giving 5D, and NFN6 represents a full field resonance network in 6D. It shows a concrete, stepwise emergence of complexity.
And the NFNs themselves, mathematically, what are they?
They arise from a generalized Noether's theorem applied to this Finsler space. For any directional symmetry, the math shows there's a conserved NFN quantity.
The coherence conservation law.
Exactly. Each NFN mathematically represents a specific conserved coherence invariant structure, like a quantized angular momentum, topological charge, dimensional step, or field phase. They are the mathematical invariants in this dynamic geometry.
Okay. How does the math handle spin, torsion, and chirality together?
There's a coherence transport equation. It describes how coherence flows, but it includes terms beyond the standard derivative. It has the Finsler covariant derivative, which handles the direction dependence, plus explicit terms for spin-induced torsion and chirality selection.
So spin and handedness directly influence the flow of coherence in the equations.
Yes, they're fundamentally integrated into the dynamics.
This leads to a pretty deep interpretation, doesn't it? The paper calls FCHP a unified ontological medium.
It does. Mathematically, this means all the physical quantities we observe, mass, time, spin, forces, aren't separate things. They are just coherence-reduced projections of the underlying FCHP structure, different shadows cast by the same reality.
Even things like measurement or symmetry breaking.
Yes, those are seen as corresponding to local reductions or changes in the FCHP coherence structure. The act of observing changes the coherence pattern locally.
And the vacuum.
The coherence vacuum is mathematically envisioned as this infinite potential base layer from which all quantized forms emerge. It's the mathematical ground state.
Does FCHP have its own version of Einstein's field equations, an equation describing the overall dynamics?
Yes, it does. It's derived similarly from a variational principle applied to an action integral involving that Finsler coherence norm.
Okay. And what does the resulting equation look like?
It leads to a Finsler coherence geodesic equation, describing the straightest paths or natural flow lines in FCHP. When coupled with matter or fields, you get the generalized coherence field equation.
And what does that look like?
It resembles a wave equation, but using a Finslerian version of the wave operator. Crucially, it includes terms for the coherence curvature tensor, Sierra, and a potential V that depends on the dimensional level, NFN. It governs how these coherence-coupled fields behave and evolve.
You mentioned chirality and spin being built in. Is there specific math for that, like operators?
Yes, there's a specific chirality operator defined, combining the standard direct chirality concept with a coherence twist operator. This operator interacts with coherent states to encode handedness as a fundamental symmetry-breaking property within FCHP.
And for spin and torsion?
FCHP uses the concept of spin-torsion coherence bundles. Mathematically, this is a fiber bundle structure. At every point in the FCHP space, there's an associated fiber containing local information about spinors, torsion, and coherence states.
Like attaching extra information spin and torsion info to each point in space.
Exactly. And there's a special Finsler torsion connection, a mathematical rule that dictates how coherence spinors, the FCHP version of electron wave functions, propagate through this space, incorporating the torsion and anisotropy directly into their motion.
So there must be an FCHP version of the Dirac equation for these spinors.
There is, the coherence spinor equation. It's a generalized Dirac equation embedded in this torsion-chiral FCHP framework. It describes how these spinorial coherence fields move through the structured FCHP space, unifying spin, mass generation, via coherence-modulated mass term, and quantum behavior rooted in directional coherence.
Can these transformations be represented with matrices like in standard quantum mechanics?
Yes, the evolution of these spinors under FCHP's influence is captured by a complex transformation matrix. Let's call it U.
And what does this matrix U contain?
It combines factors for directional spin effects, chirality rotations, and phase coherence twists. It operates within an extended Clifford-Finsler algebra, a powerful mathematical framework designed specifically for FCHP that unifies geometric and phase evolution.
Okay. You also mentioned a coherence potential V that depends on the NFN level. How does that work?
Each NFN level corresponds to a specific resonant quantization in this potential V sub n. This potential essentially defines the energy landscape for coherence fields at that level.
And the potential changes with NFN level.
Yes. The paper gives examples. V1 might be a simple harmonic oscillator potential, while higher NFNs add more complex terms. This represents a stepwise field structuring. As coherence quantizes at higher levels, richer behaviors become possible: stability layers, self-interaction, the emergence of domain walls.
So the NFN levels structure the potential energy landscape itself.
Precisely. This leads to things like stable resonance forms, phase bifurcations where solutions split, or self-organizing structures arising, depending on the NFN level and the coherence gradients. This could apply to anything from cosmic fields to biological systems.
Can it handle multiple interacting fields?
Yes, the formalism extends to multi-field systems. You can have coupled coherence fields, W1, D2, etc., interacting through terms in the potential. This allows modeling complex interference patterns and stable multidimensional coherent structures.
Like entangled quantum fields or maybe coupled oscillators in biology?
Exactly those kinds of phenomena. Coupled vacuum fluctuations, perhaps?
The paper also mentions simulations. What kind of behaviors do these equations predict in simulations?
Well, conceptually, simulations show wave propagation across an FCHP coherence gradient. The wavefronts get distorted. Anisotropic, they actually accelerate in regions of higher coherence gradient, demonstrating that direction-dependent modulation.
A direct consequence of the Finsler geometry.
Yes. They also simulate topological solitons, those stable wave packets. These maintain their structure as they move through the FCHP modulated field, representing coherence-preserving domain walls or localized transition.
And collisions between these solitons.
Simulations show they exhibit nonlinear superposition. They interact, distort sharply, but then reemerge with their original structures intact. This models things like domain wall merging, quantum vacuum transitions, or even shifts in memory structures.
How does FCHP model really complex networked interactions?
It introduces tensor resonance networks and FCHP coherence hypergraphs. The networks involve multi-layered tensor fields, allowing resonance across layers. The hypergraph is even more general.
A hypergraph, what's that?
Instead of standard graphs with edges connecting 2 points, hypergraphs have hyperedges that can connect multiple nodes simultaneously. Here, vertices are local field states, and hyperedges represent multi-node coherence relations, weighted by NFNs and coherence overlap.
So it can model complex many-body coherence relationships directly.
Exactly. It allows tracking emergent coherence corridors, defining resonance paths across dimensions, modeling complex field overlaps. It's a powerful network model for coherence.
This sounds related to resonance waveguides.
It is. These are high-coherence transmission channels within the FCHP lattice or hypergraph, analogous to optical fibers but for coherence. They allow directed transport of energy or information. Visualizations apparently show coherence flow vectors aligning along these channels.
Like dedicated information highways within the coherence field.
Precisely. And then there's coherence-based network tunneling.
Tunneling, like quantum tunneling.
Similar in concept, but for coherence itself. It's about non-local transmission coherence tunneling across barriers or discontinuities by exploiting resonance alignment along special paths called resonance null curves. Information could potentially propagate without dissipation through these self-aligned field tunnels.
Wow. Can the field itself be warped like space-time and GR?
Yes, field warping via tensor curvature. The coherence tensor sake can induce anisotropic deformation direction-dependent twisting in how fields propagate. This could lead to effects like curved coherence beams or refracted spin waves. The medium actively shapes the path.
Okay, and finally, this brings us back to computation. Coherence memory imprinting. How is memory encoded mathematically?
This is crucial. FCHP proposes that long-term coherence patterns can be literally imprinted into the FCHP substrate, stabilizing into topological memory.
Like a physical change in the coherence field?
Yes, the imprint criterion is mathematical. Memory is stored when the circulation of the coherence tensor over a closed loop quantizes to an NFN value. This forms a stable, persistent structure, a memory ring, vortex or knot, in the coherence lattice.
A quantized loop of coherence flow represents stored information.
Exactly, and it extends to multi-ring coherence holograms, superimposed memory rings whose interference encodes higher dimensional patterns. These could function as memory registers or field-based logic states, information literally etched into the geometry of coherence.
Okay, so the math provides a foundation, however complex. Now let's shift focus fully to part 2, redefining computation with FCHP. This is where the unified physics and computation idea really takes center stage.
Yes, this is where FCHP moves from describing reality to proposing how to use that reality for information processing, leading to this post-digital model.
And the core idea is that the same underlying structure, this FCHP coherence geometry, supports both physics and computation.
That's the fundamental insight. Computation isn't happening on a separate physical substrate. It's happening within the fundamental substrate of reality itself. It's intrinsically physical.
So computation gets recast as resonance structuring and hyperfractal coherence space, moving beyond just zeros and ones.
Way beyond binary.
Yeah.
This leads to the coherence logic gate framework. Forget voltage levels for logic states.
Instead, logic states are patterns.
Exactly. Logic states are defined by coherence pattern configurations, specific stable field rings, vortices, or other resonant patterns within the FCHP medium.
And logical operations, not flipping switches.
No. Operations happen via resonance reinforcement interference or phase cancellation. It's about how these coherence patterns interact. Does pattern A resonate constructively with pattern B? Do they cancel out? The result of that interaction is the logical output.
So how would basic logic gates work in this system? An A&E gate, for instance.
For an A and D, the output coherence is high, logical 1, only if two input coherence rings, say A and B, spatially overlap and they are in phase. The constructive interference where they overlap and align in phase signifies the A and D condition. It's resonance alignment.
Okay. What about an OR gate?
An OR gate gives high coherence if either input ring A or input ring B activates a region above some defined threshold. It's about sufficient resonant energy being present from at least one source.
Makes sense. How do you not?
Negation. Not is achieved by interference.
You
cancel the input coherence ring using a predefined anti-phase field. If the input ring meets this anti-phase pattern, they destructively interfere, resulting in low or zero coherence, the logical zero or negation.
Clever. Using destructive interference for not an XOR.
Exclusive. XOR produces strong coherence only when one input ring is present exclusively. If both A and B are present and overlap, they are designed to interfere in a way that cancels or significantly reduces coherence in the output region. It detects asymmetry.
So the specific interference pattern defines the logic. Yeah. This means the truth tables aren't just zeros and ones.
Right. They're resonance field configurations or resonance profiles. The truth state is the resulting spatial pattern of coherence.
Can you give an example?
Sure. For an A and D gate, input 0, 0 means no field. Input 1, 0 means a field pattern only from A. Input 0, 1 means a field pattern only from B. Input R1 results in a strong, reinforced coherence pattern, specifically where A and B overlap in phase. That overlap pattern is the true output for A and D.
Whereas for XOR, that same A1 input would result in
a region of destructive interference or cancellation where they overlap, the resulting field topology literally embodies the logical truth.
This interference principle is also key for memory, right? Interference-based memory switching.
Absolutely. For memory storage, say writing a 1, you use in-phase coherence rings that constructively interfere. This creates reinforced resonance, a stable pattern that persists.
And writing a 0.
You use antiphase rings that destructively cancel. This leads to resonance suppression, creating a null field state, the 0.
So you're using interference to actively create or erase these stable coherence patterns.
Yes. This is the basis for field-based memory registers, potentially switchless logic gates, and encoding data using phase.
The paper shows a coherence memory matrix simulation.
It does. A simple 3x3 grid where each cell stores a state based on this phase resonance. On cells show strong coherence, bright regions in the simulation. Off cells show cancellation, dim null regions. It visually demonstrates how a coherence RAM could work, encoding information spatially as a field configuration.
Okay, logic gates in memory based on coherence patterns. That leads us naturally into the next section. Coherence CPU architecture. How do you actually build a processor out of this?
Right, the paper doesn't just stop at gates. It proposes a full architecture for what it calls a post-digital computer. It starts with basic sequential elements like a sequential coherence flip-flop.
A flip-flop is a basic memory element in digital circuits, storing 1 bit. How does the coherence version work?
It uses timed coherence pulses. An initial pulse triggers a resonant response in the FCHP medium. The propagation of that coherence wave then triggers a subsequent pulse or state change after a specific delay. It's a temporal memory switch based on wave propagation time.
So the timing isn't from an external clock signal, but from the field dynamics itself.
Exactly. This allows for field-time data propagation, delayed response logic states, and synchronization using phase and propagation delays, rather than a master binary clock.
That seems very different. What about combining gates?
The paper illustrates a clocked coherence logic gate array. Imagine placing those coherence-based XOR gates along a path. A timed coherence clock pulse is sent down the path, activating each gate in sequence.
Like a wave triggering dominoes.
Sort of, yeah. The gates activate in temporal order based on the pulse arrival, producing spatial outputs that evolve over time. It functions like a pipelined logic unit, processing data in stages, but entirely using wave interactions, no transistors, a fully field-structured circuit.
How does information get moved around between these gates or memory elements? No wires, right?
This is where the resonance-based data bus comes in. It's a non-electrical channel. Information, encoded as coherence patterns, is transmitted through structured field interference patterns within the FCHP medium itself.
So the wires are actually specific pathways or channels within the coherence field.
Precisely. The field geometry itself routes the logic signals. This has huge implications. Non-local wave interference could allow simultaneous access for multiple processing nodes. Timing becomes inherently phase-aligned. You could even have reversible computing or data stored in wave loops.
That's a fundamentally different way to think about data transport. So can they assemble all these pieces into a full CPU architecture?
The paper proposes exactly that. A layered coherent CPU architecture. It lays out the components for a functional system.
What are the key components?
There's an input field interface to receive external stimuli, encoded as coherence patterns. A resonant gate array for the actual logic processing. The resonance data bus we just discussed for signal propagation. A coherence clock pulse controller for synchronization using timed pulses. A holographic memory register using those imprinted coherence patterns for storage. A phase state routing layer to dynamically redirect coherence signals. And an output field layer to emit the results as modulated coherence patterns.
It sounds like a complete system, conceptually at least. How does a signal flow through it?
The paper describes the dynamic pulse propagation. An input pulse hits the input interface, triggering a specific logic gate in the resonant array. The gate modulates the pulse's phase and amplitude according to its logic function. The modified pulse then travels along a channel in the resonance data bus, maybe guided by the routing layer. The pulse controller synchronizes its interaction with the holographic memory, reading or writing. Finally, the resulting pulse reaches the output layer and is emitted.
It's like a signal surfing on waves through different processing regions.
That's a good image for it, yeah. And it gets more complex. The architecture supports multi-channel coherence pulses.
Multiple signals at once.
Yes, pulses following distinct but potentially intersecting paths. Where they interfere, you can get conditional logic operations naturally emerging from the wave interactions.
And feedback. Can the system loop back on itself?
Crucially, yes. The paper includes active feedback circuitry. This routes output of field resonance back to earlier stages, like the input or the gate array.
Why is feedback so important?
It enables iterative computations, performing calculations step by step. It allows for conditional memory updates, changing stored information based on results. And it creates resonance-based control flow, making decisions within the computation.
This means the logic isn't just feed-forward, it becomes history-sensitive.
Exactly. The current state of the memory, the stored coherence patterns, can influence how future pulses are processed or routed. This allows for temporal logic, sequential operations, and potentially learning or adaptation, all realized through coherence resonance dynamics.
Can this architecture actually perform complex tasks like arithmetic?
As a proof of principle, the paper successfully models a coherence-based full adder logic module. A full adder is fundamental for computer arithmetic. It adds 3 binary digits.
And it works using coherence logic.
Yes. It uses input coherence fields for the numbers A, B, and the carry-in. It has layers implementing XOR logic for the sum output and ND carry logic for the carryout, all using spatial resonance patterns. A phase routing layer guides the coherence wavefronts. The output sum and carryout are themselves stabilized resonance states.
So, complex arithmetic performed entirely by interacting coherence fields. No electricity, no transistors.
That's the demonstration. It shows that the building blocks for computation are, at least conceptually, achievable within this FCHP framework.
All right, part 3, implications and outlook. We've explored the physics, the math, the computational architecture proposed by FCHP. It's fascinating stuff. But now the big questions. Is this actually valid? Is it possible?
That's definitely the crucial part. The paper frames this whole coherence computation architecture as a scientific inquiry, not a proven technology yet. But it's grounded in physical field structures, coherence, resonance, interference, rather than abstract logic states or voltage levels.
It shifts computation from abstract symbols to physical resonance patterns.
Fundamentally, yes. From Boolean toggles to coherence interference. The paper even attempts an analytical estimate of the odds of it being valid.
Oh, how does it break that down?
Well, looking at the underlying physics, coherence, interference, phase fields, these concepts are very well established. We see them in action in quantum optics, Bose-Einstein condensates, BECs, superconductors, even biological systems.
So the basic physical phenomena are real.
Yes. Real-world examples like polaric condensates or optical waveguides already show similar coherence behaviors. The main challenge isn't discovering new physics, but finding or engineering the right material platforms to precisely control these effects. So the physics risk is rated moderate.
Okay. What about information theory? Can these field patterns actually perform reliable logic?
The paper argues yes, and provides the examples of the logic gates. It shows how field logic can emulate binary logic through interference and phase. Crucially, things like XOR, AND, and memory functions have already been demonstrated experimentally in related fields like nonlinear optics. So, the information theory risk is seen as low to moderate. We have evidence wave interactions can compute.
But the real hurdle is often engineering, right? Scalability.
That's flagged as the biggest challenge. Can you miniaturize this? Can you control the coherence patterns precisely? Can you scale it up to millions or billions of gates like a modern chip? While there are related optical and spintronic systems, they aren't optimized for this specific type of coherence logic yet. So practical engineering scalability is currently seen as high risk.
And the overall computation architecture, is it a complete and viable alternative to silicon or even quantum computers?
It's still very early conceptually, but the paper makes a strong case that the essential building blocks, logic primitives, memory, data buses, control flow, are theoretically achievable within the FCHP framework. The risk here is rated medium-high, mostly because it's such a new and unproven paradigm compared to established ones.
So what's the paper's bottom line on validity?
The estimate provided is a 70–85% chance that FCHP computation is valid as a theoretical architecture, meaning the science and math likely hold together.
That's quite confident, theoretically.
It is, and practically. The estimate is a 40–60% chance that it could be realizable in a near-term engineered substrate, perhaps using photonics, or manipulating coherence in biological materials, or certain types of condensed matter.
So better than a coin flip that we might see some form of this technology emerge.
That's the paper's assessment, yes. It suggests it's worth pursuing.
Assuming it is realizable, what are the potential benefits? Why go down this road?
The advantages described are pretty compelling. First, massive parallelism. Coherence fields can interact across the whole system simultaneously. Imagine computations happening everywhere at once, naturally.
That sounds powerful.
Then there's energy efficiency. No electrical gates means potentially much lower heat dissipation. Field propagation can be very low energy. This could tackle the huge power consumption problem in modern computing.
And the memory.
Stable memory. Those imprinted coherence states could persist without needing constant power refresh, unlike standard RAM. Ideal for passive, long-term storage integrated directly into the processor.
You also mentioned compatibility with biology.
Yes, neuromorphic integration. Because it's based on fields and resonance, similar to biological processes, it might bridge the gap between artificial and natural intelligence much more easily than digital systems. It could lead to truly brain-like computing.
And the temporal logic.
That's a unique advantage. Using time and phase as fundamental logic variables allows for things like delayed response logic, built-in synchronization via wave timing, entirely new computational possibilities.
Opening up new modes of computation altogether.
Potentially, yes. A hybrid of analog and symbolic processing, field pattern AI, hybrid reasoning systems. It's a different way to think about intelligence itself.
Plus, you said it's compatible with quantum technologies.
Yes, it operates in the same physical domain fields, coherence, phases, qubits, and photonics. This suggests strong potential for hybrid systems, maybe combining the strengths of FCHP logic with quantum entanglement.
So summing up the potential.
The paper presents it as more than just plausible. It's framed as a potentially revolutionary, untapped class of physical computation that goes way beyond our current binary or even standard qubit approaches. It's envisioned as both a post-Boolean logic system and a field-based information medium for intelligence and memory, a truly new frontier.
So we have journeyed deep into FCHP Finsler Coherence Hyperfractal phase space. It's undeniably a groundbreaking framework, proposing this fundamental unity between the universe's structure and the nature of computation.
It really is. We've seen the proposal that everything we think of as fundamental dimensions, forces, mass, even time, might actually emerge from deeper patterns of coherence.
And, perhaps even more radically, that this same underlying coherence, this fabric of reality, can be manipulated, patterned, and structured to perform logic and store memory in ways that are completely different from our digital world.
It's a profound reimagining.
Yeah.
Reality not just as the stage for events, but as an active, potentially intelligent medium itself, capable of computation woven into its very structure. It certainly challenges you to rethink everything.
It really does. So the final thought you want to leave you with is this. What does this all mean for you personally? If reality truly is the shimmering, dynamic tapestry of coherence.
And if computation isn't about building separate machines, but about learning to intentionally weave complex patterns directly within that tapestry.
Just imagine what could happen, what new forms of intelligence might emerge, what new understandings of the universe could we unlock if we could genuinely learn to manipulate the fabric of reality itself, to think, to remember, to compute.
It's a truly mind-bending possibility, isn't it? It invites us all to look at the world around us, and even the act of thinking itself, in a completely new, perhaps much more integrated light.